Hi everyone. What we're going to be doing in this video is building on what we learnt in the last video, which was to do with the gradient at a point on a line. So if you remember in the last video we said, okay, if we've got this point A, we said we can work out the gradient at that point by looking at a tangent to the curve. So remember, a tangent is a straight line that's been drawn passing through A, but not passing through the curve itself. So this is a tangent, and you might recall we said, okay, if we know the gradient of the tangent, we know the gradient at that point A. Now that's all well and good if you can draw the tangent, or if you've got it drawn for you, like the questions in the book. But what if we don't have the tangent drawn for us? How on earth are we going to work out the gradient? Well, we're sort of going to get to that in the next video, but before we do, you need to learn something about what we call limits. So limits are kind of this weird mathematical idea that was invented really by the founders of calculus. And if you remember that last video, we were talking about, okay, well, you know, we said if we work out the average gradient between 2 points, what happens when those 2 points get closer and closer and closer and closer and closer and closer and closer together? The idea with a limit is we say, well, what happens as we, make that distance smaller and smaller and smaller, and the distance approaches zero? That's what we're talking about with limits. So to make a bit of sense of this, I'm just going to look at some basic functions first of all and look at the limits. And then in the next video, we're going to apply that to the gradient of a tangent. Okay, so this is the part I'd like you to write into your book. We're going to start with an example. We're going to say that f of x is equal to 5x squared plus x all divided by x. And if you went and graphed that function, and you can do that right now on Desmos or your graphics calculator, you would find that it looks something like this. So if this is the x and the y axes, this particular function is a straight line, and it passes through -5 and 5. But at this point 5 on the y-axis, this is when x is 0. So this is, x equals 0, y equals 5. At that point, x is on the bottom line. So if we substituted in 0, so if we did f of 0, we would get 5 times 0 squared plus 0 all divided by 0. Well, anytime you try and divide by 0, you get an undefined answer. So this point on the y-axis, although it kind of will look like it's there when you graph it, in fact, it's actually, we'll draw it as an open circle to show that that point doesn't actually exist, because at that point x is 0 and the function is undefined. So that particular point on the graph doesn't exist. Well, that's a bit weird. And in fact, if you did this on your graphics calculator and you tried to find the y-intercept, it'll say undefined. That's a bit weird, but what we can do is we can say, well, we know it's undefined and there's no solution, but what if we just get really close to it? So if we say the limit as x approaches 0, so this is a new piece of mathematical notation. Lim means limit, x arrow 0 means x approaches 0. So this means x approaches 0. The limit as x approaches 0 of f of x, well, that's a different definition. That isn't saying what is f of x when x is 0. It's saying what happens if we get really close to 0, what is it going to be? And that definition is different. In fact, this definition says that it's equal to 5. Because if we were looking at that really close up, so if this was the y-axis, and here's 5, if we were looking at that graph, if you started to get closer and closer and closer and closer and closer to that axis where x is 0, we would say it's 5. If you actually just went straight to it, it's not going to exist. But if we get really close to it, you're essentially at 5. So that's what we say is the definition of the limit. And the same thing works if you come at it from the other way. If you come at it from this direction and get really, really close, you're essentially going to get 5. So it's a little bit of a weird concept to get your head around, but that's what we're talking about when we say limits. I'll show you how to work out what the limit is algebraically now, and that's actually fairly straightforward. Okay, so algebraically, let's say we want to work out the limit as x approaches 0 of, let's go with a simpler function than the one I just did. We're going to say x plus 2. Well, in this case, things are really simple. The function x plus 2 is defined at x equals 0. It's fine to put 0 in there. So in this case, we simply substitute. So we just say that's equal to 0 plus 2. So the x is just, or the 0 rather, is just going in where the x is. And that's equal to 2. Very simple. Slightly harder case. Well, let's just do the one I just did as an example. The limit as x approaches 0 of 5x plus x squared over x. So I showed you the graph of that, but we can actually do that algebraically as well. So what we do, we've got this x on the bottom line, which is causing us issues at x equals 0. It's undefined. So what I'm going to do is I'm actually going to divide the top line by x, because that's what this means. First of all, I might just take x out as a common factor on the top line. So we can rewrite that as x, and then in brackets 5 plus x. So I've just factorized that little quadratic there over x. And now these two x's will cancel each other out. And we're just left with 5 plus x. And it's okay for me to do that because we're approaching 0. We're not saying this isn't when x equals 0. Because if I divide by 0, it's always undefined. But x doesn't equal 0 in this case. We're just getting really, 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 really close to it. So here I am. I've got 5 plus x. Now I can just substitute in 0. Okay? So now that I've gotten to this point, I'm allowed to substitute in x equals 0 because it is defined when x equals 0. So that's 5 plus 0, which is 5. And that agrees with what we did on the graph earlier. Okay, I'll do one more example just to show you that it's not always 0 that we're going to approach. We could be approaching 2, for example, so x approaching 2. And I'm going to put on the top line, we'll do a tricky one, so we'll do x squared take 4 over x take 2. Well, in this case, again, if we put the 2 straight in, that's going to be undefined. It's going to be 2 take 2, which is 0. That'll be undefined. So I need to simplify this and get rid of that off of the bottom line. Luckily, we all did quadratics in semester 1, and we know that x squared take 4 can be factorized as x plus 2 multiplied by x take 2 all over x take 2. And now again, I can do some cancelling out. So that x take 2 cancels that x take 2 on the bottom line. Again, I'm allowed to do that because I'm not saying that x is equal to 2. I'm saying that it's getting really, really, really close to 2. So now that we've cancelled those out, we can say that this is the limit as x approaches 2 of x plus 2 which is simply equal to 2 plus 2. So I'm allowed to substitute that 2 in now, and I get 4. Okay, so I hope that makes sense. The key thing to remember when you're working these out is if there's nothing on the bottom line, you're generally safe to just substitute the value straight in, just like evaluating the function at that x coordinate. If you do have something on the bottom line that's causing you issues, you'll generally need to factorize the top line, and then you can cancel two things out. Okay, I hope that makes sense. We're going to use that to do exercise 14C.1 in class. Okay, thank you very much for watching.